Thank you.
Our next talk is going to be from Kris Zacny, Planetary Volatiles Extractor.
Thanks very much. Yeah, I just made it after landed like an hour ago in NESF. So you guys doing an excellent job telling us where to go and mine and excavate water and make money out of this. And my presentation here is going to be essentially about how to extract volatiles in water and potentially how to make a lot of people wealthy. This thing is advancing by itself. I don't know. Yeah.
Was that picture of you lounging in the chair while your bread's
Yes, exactly. Exactly.
That's what we have to let our elves in the back deal with that. I guess
Can we go to the first slide? Okay. Do I use this?
Yes.
Okay. So obviously, I don't have to state obvious. There's plenty of water everywhere we look, which is really good because depending which way NASA goes, we have water. And what this means, the technology that we're developing right now is applicable to both Mars, Moon, and asteroids as well. So this is actually old slides, but okay. So how would you mine water ice? And there's two types of ice. It's a hydrated, obviously, water, which where you mine regolith, and the bound water, which is essentially frozen in some kind of a matrix. So to learn how to mine the most difficult water, which is a bound water, we go to Arctic and Antarctica. So this is example of Arctic. Here, water essentially percolated down and froze over the years. We dig down the trench of a burden, get down to a frozen water ice, and what we usually find is this frozen water ice, a frozen soil with water is as hard as concrete. We use the pick. That's my grad student. I'm sitting right over there, and he clearly couldn't penetrate this hole right over here, so he failed. I failed him. We also go to Antarctica, and Antarctica is a slightly different beast because in the dry valleys, water inside the soil matrix is actually vapor deposited. So it's sort of what we see, for example, on Mars or the Moon. And you think that this frozen, permafrosted soil with ice or ice-cemented ground would be any different. Well, it's not. These are the pick marks, trying again to dig into this formation, and you can't. It's super hard like concrete. Here is example of a JC1A, which is a lunar simulant, at only -20 C. And here we used this is a percussive hammering scoop. Uses something like close to 5 joules per blow, which is much bigger than most of the Home Depot drills. It's a lot of joules at 1,800 blows per minute and 3,000 Newton force, and we could barely penetrate these formations, only at -20 C. And why is that? Well, if you look at the unconfined compressive strength in MPa, this tells you how hard formation is as a function of water content at liquid nitrogen temperature. Very quickly you realize there is this curve that shows you it goes all the way to around 100 MPa for a fully saturated sample. Just for reference, concrete for commercial structures, it's much harder concrete than what you use for building smaller buildings, is around 30 MPa. So 30 MPa is concrete. Water formation with water content of around 8% is around 40 MPa. And if you have fully saturated soil at LN2 temperatures, you're around the strength of basalt. Well, if you switch gears and you look at strength of ice, for reference, this is the same concrete, around 30 MPa. This is a temperature. If you go to very cold temperatures, ice itself is much harder than concrete. So if you go to the Moon, Mars, or other planets, and you have ice which is locked in a matrix, you're going to have a hard time digging it. But normally in the hard formations, concretes and so on, you use drills. And in the same site, in the Arctic, we used drills, different shapes and sizes. We had no problem penetrating the same formation. When we went to Antarctica, we couldn't dig with picks, but we had no problems drilling with this percussive drill using only 100 watts of power. And in fact, the stuff that was coming out, these icy cuttings, they behaved like sand on the beach. So if the temperature is really, really low, you're not exposed to direct sunlight, the icy soil behaves like dry sand on a beach. If you warm it up, you expose it to sun, that's when it becomes sticky. But as long as you keep everything cold, there is no stickiness. And that's what a lot of people are worried about, that icy soil is going to be sticky. No, it's not. It's not sticky as long as the temperature is low. If you go to Antarctica, you cannot make a snowball because it's so dry. It's only when the temperature is higher, when you have a higher humidity, that's when you make a snowball. The same JEC1A, this is the scoop with good stock. This is a drill, matters of second penetrated down. So we used our water extraction system and we built it around the drill. And there are a few approaches to mining water. First one is the central process with standard sort of a mining process where you have tracks, crushing some soil and so on, then transporting to a processing station. You have a processing station, and then you extract good stuff, and then bad stuff is transported to some kind of a tailings. The second approach is sort of like a continuous mine approach, where you ingest your feedstock, you do all the processing, you dump the bad stuff behind you, and you capture the good stuff. And obviously, there is in my opinion, there is a lot to say about processing everything in situ versus going back and forth. If you go back and forth, especially with water ice on the moon, a lot of water is going to be lost due to sublimation effects, and we've seen it in a vacuum chamber. On Mars, it's not a problem. If some of you witness Phoenix lander, there was ice on certain sol on the ground. Next day, still the same ice. Third day, also same. Under lunar conditions in a hard vacuum, ice actually sublimes very, very fast. You blink ice, it's going to be gone. So we looked at the three different extraction options. Sniffer, it's sort of, we used this because everyone was talking about it. Everyone thinks drilling down with perforated sort of auger, heating it up and trying to pull volatiles through these holes into the cold finger is actually going to work. We knew it's not going to work because water usually goes to cold finger, to a cold trap. If you heat up these surfaces, you're going to repel water effectively, and water is going to go somewhere else. But we tried it just to see what happens. Another one, we call it the Miswi mobile in situ water extraction system. It's a deep fluted auger which you use to drill down into the subsurface. You capture volatiles, you capture entire soil, you move it back into this reactor, you send heat from the RTGs, you heat up the soil, capture water on a cold finger, you dump the soil, and you move on. And the third one is a coring system, where this is outside corer with the internal sort of copper with perforations. You drill down, you capture a core, icy core, you heat up the core itself, capture volatiles flow in this annular space between the copper and the outside auger, you capture onto a cold finger. When you're done, you pull it out and you go to the next spot. We did all the tests in a vacuum chamber. So we had, this is a small vacuum chamber, so everything was scaled down. We used JEC1A soil. This is our experiment in some kind of a soil. This is water vapor flow through a hose into a cold finger, which was sitting in an ice bath. This is a setup for a sniffer. So that was 3D printed sniffer inside the soil, wet, icy soil. That's our transfer tube into a cold finger sitting in an ice bath. The close-up right over here, we use different parameters and so on. What we found is what we expected. The soil on the outside heats up, sublimes, and blows the regolith out of the way, and the regolith essentially drops on the outside. So it does, the water vapor doesn't actually go inside the sniffer. It escapes on the outside, essentially. We couldn't get much. This is set up for a Miswi. We had one design with just a plain augers, another design with sort of heat spreaders with these spikes. The issue with, I have 2 minutes. All right, so I have problem. So anyway, this actually worked pretty well. You see, we got some water. Then we tried a coring setup, which we thought is going to be most efficient, and that's a 2-inch coring system inside the soil. It also did a bunch of different tests and actually worked the best. So if you compare all the 4 different designs, the coring is #1, followed by the Miswi with these spikes as a heat spreaders, putting heat more inside the soil, followed by just traditional auger, and sniffer is the last one. From a drilling standpoint, this is the coring system. This is all like a sniffer or Miswi system. You can just, by looking at the 2 different architectures, you can see that from a drilling standpoint, this one will require way more energy and the forces and things like this to penetrate subsurface versus this one. Here we're just cutting an annular space, whereas here we have to cut entire surface. So from an energy standpoint, you are order of magnitude more efficient right over here than here. We've done some efficiency studies for all the different designs, and this is a final design that we're actually building right now under SBIR phase 2. So it's a rotary percussive drill head with a coring system that's going to be around 0.5 meter long, 2 or 3 inches diameter. It's designed to mount on a Curiosity-sized rover. This is for scale right over here, and this is our cold finger. And in the future, we're going to run tests inside a vacuum chamber. From a power standpoint, power is obviously always a question where you're going to get it from. We did analysis, and bottom line is we need 2 MMRTGs, so Curiosity-sized RTGs, to provide required heat to extract water and provide required energy to actually drill down. So the math actually checks out. I'd like to acknowledge SBIR program, NASA, Kenneth Johnson, Jerry Sanders, and Aaron Pass. And thank you very much.
Okay, we have time for questions. I see people. Let's see. What's it? Go ahead. You are the chair.
So you mentioned, I quoted you when I wrote this note, icy soil isn't sticky. I saw a video recently for Resource Prospector where they were putting the lunar simulant in a funnel and shaking it, and it gets stuck in the funnel. It didn't have any water in it.
It's cohesion.
It's cohesion. So how does the cohesion, if it's icy but the same kind of character that has that same cohesion, does the ice help? Does it help it for, not stick?
Whether ice will reduce cohesion, if that's a question.
Yes.
Probably yes. What happens, the reason why soil is cohesive, the soil that you've seen, is because the particles are really jagged, and actually lunar soil, the old one has 50% agglutinates, which are even more jagged. So lunar soil has so-called apparent cohesion. The true cohesion is actually due to water here on Earth, where you have surface tension. When you get water on the grains, my feel is that water is gonna bound itself and make the particles more smoother. So if you look under the microscope, it's gonna look more like a sphere rather than like a needle. Whereas crushed basalt or lunar soil it's very jagged. That's why it locks. With ice, if you have ice on the individual particles, it's gonna be more smoother, so less cohesive as well.
Yeah, I know you guys have also done sample return ideas and stuff. Have you incorporated this core in a sample return, and do you know how much water you lose again in that process, or is that?
So So we've done some coring in icy soil in a vacuum, and we don't lose a lot. Maybe it's like a fraction of a percent, but it all depends what happens from the moment you pick up the core to the moment you actually cache it, and the thermal environment is very important. So if you drill in an icy soil, let's say 60 Kelvin or 80 Kelvin, and you don't raise the temperature above say 100 Kelvin, you have no problem. But once you remove it and your drill sits in front of the sun and heats up a little bit, that's when the problem happens. Okay, the sublimation becomes exponential. So I'm not worried what happens during the drilling, but what happens during the transfer.
Thank you very much.
Thank you.